better than hand-coded C, right? Well, some people, especially C fans, would say that's an oxymoron, right? That can't be, because whatever you program in fancy C++ metaprogramming, you could program that exact same thing in C, and then it'd be the same speed, right? So you can never beat C. But in reality, there are actually trade-offs. There's, most of it is programmer productivity trade-offs or readability, code reviewability trade-offs. Whereas in my opinion, code reviewability and readability trade-offs are the most important ones that stop you from unleashing the full potential in C. Because in C, everyone on the whole team sees your code, right? You can't review your code in isolation. Some novice programmer who just joined the team can do terrible things if he doesn't understand your code, right? It's not encapsulated. The most important thing you can do in metaprogramming, in my mind, I mean, you can make stuff faster, you can, but the most important term in metaprogramming, the most important marketing term, if you will, is encapsulation of expertise, right? I know how to do it, and I can put that knowledge in a bubble, and you can use, or in a library, you can use my library without knowing my expertise, right? And this only works if you can do zero-cost abstractions. I mean, it does cost stuff in, non-optimized code because it's a function call, because it's some extra stuff. But this is all stuff that we know and can prove that the optimizer is going to, the function will be inline. It's in a header, it's templatized, so no external linkage. It's going to be inlined, right? We can even force inlining them, but there's still no force inline syntax that's standardized. So we don't do that because we know the optimizer is going to do it anyway, right? So because we can create these zero-cost abstractions, we can encapsulate expertise. So if one person thinks of one way to optimize something, then put that in the library. Everybody profits. Most people don't even know it's happened, right? So we can do the as-if rule. I mean, nobody really understands the optimizer anymore except the people that made it, and even then, I don't know. But it's encapsulated expertise, and this, again, we can encapsulate expertise. So we can do a thing called bit banding, which basically is a special part of the ARM architecture. It's only available on ARM processors, but ARM revolution is still ongoing. That's going to be like every processor soon, right? Very big market share. So bit banding, we take the address range of special function registers and make larger address range, which is kind of a shadow of special function registers, except it's 32 times bigger, and every address is a bit, right? So I can take the address of a normal register and bit offset, use that to calculate, well, what address do I have to write a bool to set or clear this bit? You can also read using bit banding. Problem with that is, code readability just goes down the drain, right? Oh, there's this other thing that's somehow the same thing as that thing I just wrote, right? Completely different address, and it's showing up there. And it's way more typing, which is probably the real reason why, if you look through GitHub, out of the several thousand repositories that contain some ARM assembler keywords or something that isolate other repositories, that you come up with a couple thousand. And if you look at addresses in the bit banding space, you come up with 3. There's only a couple people using this, because you have to learn how to do it, you have to teach everybody in your team how to do it, and it's still ugly, and it's still way more typing, right? But we can do this under the covers, and nobody has to know, right? If we're, rather than reading a register, masking off some bit and then writing it back, we can just clear it by writing a bool to one of these registers. It's blind write somewhere rather than read, modify, write, more efficient, right? Only really is good if you're writing just one bit, because otherwise you have multiple writes to different bits. Plus there's an as-if rule problem there, because sometimes it is observable from the outside if one bit was written before the other bit. You know, if they give us a 2-bit can mode, and we write one of those bits first, then we're going through another mode for one instruction cycle, which may trigger something, right? But for single bits, it's great. Then we have blind writes. You know, blind write means we basically prove that in, you know, not the whole 32 bits of the register, but maybe an 8-bit part or a 16-bit part, because the Cortex cores can write in 8-bit mode or 16-bit mode as well as 32-bit mode. So, well, you know, what's the smallest size that covers all the bits that in question, and how about the other bits in that range? If they're reserved, if they're read-only, if they're set to clear, or for some other reason there's a default value, then we can just write. We don't have to read, mask, modify, do stuff, write. So that happens, you know, it happens actually more than you would think, because, you know, if it's 1 bit, well, we use bit banding. If it's multiple bits, well, then there's going to be some bigger fields in that register usually, and they usually kind of align them to 8 bits by padding them with reserved bits. I mean, the hardware guys actually did a pretty good job on most of the processors I've seen. You know, if you got like a 5-bit value, well, they'll put 3 reserved bits next to that, and thus we can turn it into a blind write. Temporary is encouraged by the interface. I got a slide for that. What I mean by that, reordering access. Again, I've got a slide. If you sort the accesses by address, then there's some optimization potential there. And merging, we'll see what that means in a minute. So local temporary is encouraged by public interface. If we have a register and we want to test some masks against this register, we want to figure out, is this bit set? Oh, is this bit set? Then we can either do that directly, or we could read it into a temporary and then test against the temporary. And testing against the temporary is actually more efficient, because you know, reading over the bus from RAM is usually multiple instruction cycles, whereas reading from a local register is just one instruction cycle. Plus, the temporary isn't actually using any resources. I mean, res is a work register, right? We have to load it into a work register anyway before we really do anything with it. So we're not actually using extra variables here. In this case, we're reading 2 things, right? Thing 1, thing 2, both bits in the same register. If there were different registers, this would still work, but it would be less efficient. Same syntax though. So this is basically an unsigned integer, which is what we read out of this, and then this becomes masking them off, right? So we're still reading the value, masking off all the bits that we don't care about, and seeing if it's a 1 or a 0. It's just we've encapsulated this into sort of a tuple kind of a pattern, right? In the standard library, as of C++11, we have a tuple of values, and we can get them by index with the global get. So this is the exact same syntax you'd use as if you're using the standard library tuple. What we also could do, you could also, instead of writing 1 in pointy brackets, you could also write comma thing 2. So you can also index by type out of your tuple if you want. And this is just as efficient as handwritten C code, but it's type safe. You know, if, say, this was clear on read, thing 1 or thing 2 was clear on read, we wouldn't be able to say read here. We would have to say read and clear would be the name of the factory. So in code review, we can prove that we're not screwing up here, right? Nothing unexpected is going on. Then we get to reordering access, and this is actually probably the most complicated part of this optimization section. So this is basically the ARM assembler command for reading a literal. You know, you can load from an address, but this address, you know, how do you load the address if you can load from an address? Well, the address is 32 bits, and commands are also 32 bits, or even 16 bits in Thumb2, right? You can't load a whole 32 bits in one instruction cycle then, unless you use this trick. you basically put your literal somewhere near you, basically at the end of the function. You put it in code, and then you load the program counter with a offset. So you basically just load that value right out of Flash near you, right? Because the program counter is pointing to where you are, and if it's 20 instructions down the road, well, we'll just do an offset of 20, and then we can load it in one instruction cycle. So it takes 2 words of data and 1 instruction cycle. So that's basically the most efficient way to get the address of something. Now, once we have the address of something, we can also load other things with this offset, right? If we were to do this, reg 1, reg 2, reg 3, I'm going to just say we don't care about the order here, right? There's nothing fishy going on under the covers. We just want these to be added to those registers, and I don't care about the order. In normal C++ or C, there's no syntactic method of saying I don't care about the order for a volatile register. I mean, volatile means this store has to happen before this load, right? Loads and stores can't pass each other up, right? The optimizer can't reorder here to make this more efficient. And that's good because a lot of the time it does matter. Like, I want to set can mode to configuration mode and then write to this configuration register, because otherwise I'm going to get an error if it reorders that, right? If I write to the configuration route before switching the mode, right? Or if I'm writing to port pins, right? Obviously I want one thing to happen, I want data to get there before read strobe goes up, right? Or write strobe, sorry. So most of the time we care, sometimes we don't on a very small scale. I mean, if I'm writing to some can configuration registers, I probably don't really care what order I write to like the 4 registers in, as long as it all happens after I put it in configuration mode and before I take it out of configuration mode, right? But there's no way to syntactically express that. There is kind of a workaround, which we see here at the bottom. So in the middle here, I'm accessing an address which is kind of far away. So I do this trick of, load from a literal pool to do this. And then I load my literal again, and then the question is, do I still have that temporary, I had the address of this is right next to it, is a small offset, is that still in the work register? Well, there's 14 work registers that you can use freely, but on the other hand, only 4 of them are ever pushed to the stack in a function call. So you usually only just have 4, unless you want to do expensive pushing of more to the stack. So chances are actually pretty high that you don't have this address anymore down here, or down here as it were, right? So we're loading from our literal pool 1 too many times. If we were to switch these 2 around, then we'd load from our literal pool 1 less time. We'd be more efficient by switching these 2. So that's actually why we're doing reg 2 down at the very bottom here. But the other thing we can do, we also have these load multiple, store multiple. And we're really hitting the optimizer over the head with regard to that, because you can't ever do a multiple if everything's volatile, right? Even if they're right next to each other. Because we're saying to the optimizer, you have to store this one before you can load that one. So it can't ever do them simultaneously. Well, we could do this simultaneously in several steps, and this code would be much more efficient than this code, because this would be a load multiple, we do this to work registers, this would be a store multiple, right? The reason we don't do this, I've never seen anyone do this in code, and I've looked at a lot of other people's code, right? The reason is, anyone see the bug? I put a bug in there. I don't actually see it myself anymore, to be honest. So wait a minute, so we got reg 1 is plus equals 4. Oh yeah, I switched around 5 and 6, right? That could easily get through code review. And even if it doesn't get through code review, a bunch of people spend time figuring this stuff out, like, just buy a more powerful processor, right? Or use Kvasir, right? Because we don't actually do this yet, but we will. We can do it with the same public interface. It's just a back-end optimization that we can add later. So people watching the video, it probably already works. And then we come to merging access. So this is actually an optimization you will see in user code. If I'm accessing two separate bit fields in one register, then I can just merge the masks, right? Okay, I'm clearing this bit and I'm clearing these 2 bits. Well, I could just clear all 3 of those bits, right? I'm setting this bit and I'm setting that bit. Well, I could just set them both together. It's all the same register, right? So you will see, user code, I don't know, auto reg equals, well, they do like unsigned reg because they usually don't use C++11. So unsigned reg equals the register, reg or equals this mask or this mask or this mask or this mask, and then, for the clearing bits, inverting the or together masks. It confuses a lot of novice users. You'll see stuff on forums, oh, well, what are they doing here? Or, I got this value that's going to this register, but I don't find it in the data sheet. What are they doing? Well, it's these 2 values together. So, it is used. It's probably good that it's used, but it's a trade-off. It's a design decision, whether to do that or not. We can do it automatically, right? If you go back to our code, if we were doing 2 LEDs at the same time, and they were on the same port, they would just automatically be merged. The biggest merge potential is actually at startup, because you typically have a huge amount of initialization of hardware where, okay, I'm turning on power and clock for 10 different peripherals, right? But I'm doing this nicely encapsulated in 10 different classes, right? So in class 1, in the constructor, or however you end up abstracting it, you're loading from a literal store the address of the power register, setting 1 bit, throwing away all that information, 100 lines of assembler later, you're loading that same thing and then initialization of the next class, and again and again and again. Whereas if you were to merge them, the first one would cost the same amount and all the other 19 would be free, right? Plus, the first one might even cost you less because there might be a register next to it. I mean, if we merge the initialization of every class in the whole program, then there's going to be clumps of registers next to each other. I mean, we could even go so far, we don't do this yet, but we could even go so far if there's strings of registers right next to each other, we could even make our own literal store and just do a block copy into the registers. It's also added functionality because I can detect initialization conflicts here, right? Different mod, if I've got a couple of UARTs and something else, they're accessing power clock, they're accessing bus clock timing registers and stuff, which are shared between all these objects. I mean, it's a unique situation in an embedded field where I'm sharing registers on like a global scale, and if there's a bug in my 3rd UART, and I only have 3, and the one that's being initialized the 3rd, well, then nothing works. But if it's the 2nd or the 1st, it's going to be overwritten by the 3rd, and initialization order of global object is undefined, right? So it could, I could suddenly start noticing this bug like a week before release or something, right? I mean, it could pop up at any time, these initialization bugs, so they're really nasty, but if everything's going into the library, I can detect, oh look, 2 people are writing different things to the same register. Issue an error message, plain English, right? So this is this merged initialization which I'm talking about, right? The startup code is something unique to the embedded field. Basically, God created main, right? Well, there is something before main, and that something before main is, initializing objects, turning on RAM. I mean, sometimes you even have to turn on RAM, setting up the clock, setting up all that kind of stuff is done in so-called startup code, right? Initialize the heap, initialize the stack, set up all the interrupt service routines because they're just mapped into this defined space of an array of function pointers for interrupt service routines. Do that kind of stuff. And there wasn't really a good way to do this before C++11. The LPC Open library, basically you copy a file called cr_startup something something.c into your project, and it then does this magic. You can't really put it in a library because sometimes it's modified by macros, and library code is precompiled, so you couldn't really do the macro stuff. So that's, it's a pragmatic decision. Embed does it differently. Embed, you run your nifty Python script, which I still haven't gotten to work, but that might just be because I'm stupid, I don't know, probably. But it's definitely a pain. So this Python script, builds everything together and puts in your startup code. And if you look on online forums, there's a bunch of people like, what's this CR something something that I have to copy into my project? Or my project, I never enter main. Well, you need that CR something something, right? Or what's in there? I mean, it's full of macros. It's just definitely not novice friendly code, and there's a reason for that. It's got a bunch of implementation defined code. Yeah, it's pretty nasty. Well, what we do, basically, is rather than making the user include a file, well, he's already got a file, main.cpp, right? We already have to require him to tell us which classes have initialization data for merged initialization. Why don't we just use that macro for two things and just put, inject all the startup code into that macro, so it just expands into your main.cpp file. We can also hook up ISRs, so basically you just put a tag in your class, just a const expr variable called init and a const expr variable called ISR, and tell it which ISR you want and what your init is, and it'll hook it up magically. Or not magically, but with metaprogramming. We can configure the system clock during startup. That's actually, Kvasir start is one macro, and the system clock configuration macro is the other macro. Only two macros in Kvasir. The advantage to configuring the system clock in a compile time known method is we know at compile time what the frequency of the system clock is, right? So if we're calculating baud rate, people can give us the baud rate they want, and we'll do all the calculation under the covers because we know what the system clock is, right? We can also gripe about clocks being out of range, out of spec for the chip. I mean, that stuff hasn't been programmed yet, but could potentially be added to the back end as special error messages. Again, it's got to be fully flexible. People have to use all the functionality they want. So there's every step that we do something, there's a hook in between there where a power user can specialize a template and put his code there, right? So it's still fully functional. You don't actually have to go through this terrible library. There's just a couple of templates that you specialize to get your code into wherever you want. Usually you never have to do that. Then we have the general architecture of a library has the same problem that usually you need a build script or you need like 20 different versions of your library. The LPC Open library, you download the LPC Open library for your specific chip, right? And that's got a bunch of redundant code in it. There's like a bunch of different LPC Open library versions that all share most of the same code. And the reason for that is generic code needs to include chip-specific code. And so, but if you're using a different chip, that chip-specific code might be different. And so there's two ways to go at that. You write generic code and a bunch of different versions of your chip-specific code, and for every version of your chip-specific code, you put all the generic code in there too and give it, ship it. Or the other way around, you write generic code and have a Python script select the right chip-specific code, merge that, it's part of your sort of initial learning of the library process, I'd say they're both suboptimal. I mean, the people that made them was probably the best design decision with the constraints, but I'm going with different design constraints, right? As soon as you have C++ templates, you can what's called specialize a traits. And a traits is basically specialized template, just like a meta function. I mean, at the end of the day, it's all specialized templates, but the design pattern is different. I provide the generic case up here of my template. I can use that generic case or reference that generic case in generic code. I can specialize that generic case for a tag that I know that I'm using. In this case, we'll say void, right? I've got generic case takes a type name. Here, I call it with void and want its type for me. Here, I specialize for the type void, which I know I'm using, and give it the chip-specific information. So, intuitively, you'd say, well, this would get that version. Well, not really, because there's this thing called point of instantiation, which is basically, I talked about it earlier, it's where the template actually gets made, right? It's not made here, still has template parameters here. It's not quite as easy as that, but that's the easy shortcut. As soon as it no longer has template parameters, as soon as all the template parameters are actual things, then it's instantiated. That's the point of instantiation. So that's way down here in user code where we've already included this one too, right? So the specialization is visible. And the user could forget to include this file, and to make sure they don't get an ungodly template error, we make the generic case, if it's ever used, all it does is issue an error saying in plain English, you need to include a chip file, right? So it's pretty robust. And again, all you need to do, download Kvasir, add it to your include path.